Bom dia.
Bom dia.
Opa, bom dia. A gente tava testando aqui uns vídeos pra gente deixar rodando aí, quem sabe quando tiver um tempo de descanso.
Ah, tá bem.
A conferência deve começar logo mais, mas a gente
Aham.
vocês podem ir fazendo. Só lembrando que vocês podem usar a sala de ensaio lá embaixo para poder fazer algum teste de apresentação, se vocês quiserem, tá?
Ah, tá
Agora,
ok.
Júlio, a gente pode começar, né? Já botou no YouTube?
Já botei.
Ah,
Tá rolando no
excelente.
YouTube.
Então ainda tenho uns 2 minutinhos. O primeiro, the first paper is from Dunfrey Aragão.
He's here already.
Ah, okay, he's here. Cass is here. Then, okay, then the next authors will come.
Did you put in YouTube, Julio? Let me see there.
Yeah, it's there. It's there.
Okay.
Okay.
Okay, welcome to the first session of LARS in this Tuesday. The session is vision sensing and mapping. The second session of vision sensing and mapping. The first paper is a recurrent multitasking network in robot relocation that will be presented by Dunfrey Aragão. Dunfrey, do you prefer to play the video or are you going to present live?
Could you please play the video?
Okay.
Just a second.
Mhm.
It's mute, Julio.
Hello, my name is Dunfrey Pires Aragão, and with the Agnes
Okay.
we would like to present the work called Comparison between two recurrent multitask networks for robot relocation.
We are
This
not
work
seeing
has the support
the
of the
screen.
Federal University of Rio Grande do Norte.
It's mute, Julio.
Hello, my name is Dunfrey Pires Aragão, and with
Not
the
sharing.
Agnes we would like to present the work called Comparison between two recurrent multitask networks for robot
Hello,
relocation.
my name is Dunfrey Pires Aragão, and with the Agnes Mentor, we would like to present the work called Comparison between two recurrent multitask networks for robot relocation. This work has the support of the Federal University of Rio Grande do Norte and the NataNet Labs. The work aims to address some issues in the field of robotic map exploration, including how to determine where the agent or robot is on the specific map, the quaternion, which represents the robot orientation, and depth in discernment of objects in the view, for distinguishing objects and avoid the potential issues such as occlusions. This last one is an important field because even if a robot is walking in a known environment, if someone appears in front of the robot, for example, it is an unexpected situation and the robot doesn't know what to do. Is it to stop, or will it go to the right or even turn left? During our research, we discovered a state-of-art network called PulseNet, as well as an enhancement to this model called ContextualNet. It means ContextualNet is the PulseNet with LSTM layers that performs better in robot pose regression. So we worked on creating an alternative to ContextualNet that could also regress a new task. We discovered SpaceNet, a model capable of regressing the depth scene and the robot pose at the same time. The SpaceNet is built using autoencoded architecture in part of Google Net architecture. The first part of the autoencode is responsible in this model for assembling the latent space and generating the code map. And at this component moment, which will be divided here, we'll divide it in two distinct responsibilities. The first one is used to generate the depth scene image. And the second one goes to the Google Net, which employs convolutional layers. And at the end, we attach two stacked LSTM layers for pose regression. And so, the pose regression and the depth scene regression are then addressed. To evaluate these models, we use two different datasets. One provided by the Laser Lab, which used a turtle boat running around the laboratory with 30 meters per 40 meters to capture RGB image and the depth scene labels, as well as the odometry labels given by the robot's wells. And the second one, called RGBD Scenes Dataset version 2, which includes furniture images such as sofa, chairs, coffee tables, and others. For all images, a pre-processing pipeline was applied. A data rescale and normalization were required, transform the image pixels levels ranging from 0 to 1. Following that, we disregard the z-axis in the data containing in the laser dataset because we are talking about terrestrial robots, and as a result, we assume that the robot has a constant z-axis value. The route labels, which are the location and the orientation, are missing from the RGBD scenes dataset version 2. So, to create them, we use the same approach that was used in PulseNet to generate the route for each image sequence using software called Visual Structure from Motion System, the VSFM. And finally, the 6DOF generated by the RGBD scenes dataset version 2 and the laser dataset were standardized, applying the Z-score approach. The results produced using the laser dataset shows that the SpaceNet version 2 has significant enhancement when compared to the original version without LSTM layers. We observed that the regressing all axis and the orientation, the use of LSTM improves the regression. Also, we observed the network produced outcomes with similar accuracy than ContextualNet, closer to the ground truth, especially in regressing the x-axis and the orientation, as observed here. For the RGBD scenes dataset version 2, the evaluation shows that the SpaceNet could also be an alternative for contextual.net, being better in regressing the axis X and Z, and contextual.net is better regress the Y in the orientation. The depth scene generated by the SpaceNet shows being good comprehension in comparing to the ground truth may be an acceptable outcome as a result. Finally, we can observe that both networks, SpaceNet and contextual.net, present a sort of noise and some inaccuracy in regressing pose in general. In conclusion, we observe that SpaceNet can preserve the depths in prediction information and its characteristics vectors. Even the network has some difficulty in converging the results because it has a new task to be regressed. The network has demonstrated that it performs all activities with some degree of success. Also, the network shows being an alternative to contextual.net in post-regression, and also can do the depth scene regression. And is it? Thank you for every attention and have a good one day.
Thank you, Danfrey. Very interesting work. Anyone has questions? No? Well, I have a question. Do you use in your multitask recurrent network the encoder is the same for depth and for pose estimation?
Yeah, the first part of the autoencoder, né?
Is the same. Okay.
Yeah, in the latent space, we divide for both regressing tasks. But at the beginning, yes, the first part is shared for both tasks.
Mm-hmm. Okay, and have you used an LSTM also for the depth or only for the pose?
Only for pose. Yeah.
Only for pose.
To depth scene regression, we just use the second part of the autoencoder. And for regressing, we use GoogleNet. At the end, we attach LSTM layers.
Okay, very interesting. And what are the main challenges that you faced when training those networks and also testing?
The main challenge, for sure, was to take a good data set. Sorry, a good data set, because in some data set we don't see this kind of composition, RGB image, depth scene, and the Wells odometry or something like that. And finding this kind of data set, it's a really bit hard. Like, for example, the Kitty, they don't has a single data set with these three composition. Sometimes the RGB and depth scene, or the RGB and the odometry. I didn't find these three compounding one single data set. And the processing data as well. The training wasn't hard at all, just computations. So everything was okay. It's about the data set, the hard part to do.
At the end, did you collect your own data set, or have you used?
One we find the RGBD data set we find at the internet, make some researches, and the first one, the laser data set, we produce it at the lab laser at Federal University of Paraíba. We made it.
Okay, is it available or not?
Yeah, it's available. It's available.
Okay, interesting. And have you considered using it outdoors or only indoors? Have you tested only indoors?
Yeah, for sure. We are interested and we will apply the model in outdoor scenarios. in which we have more differential lighting casing, but we wanted to first evaluate these modeling situations with some kind of features management or situations with more control. And then we try to apply them to data sets like Kitty or NYU DEC version 2, you know?
Yes, yes. Okay, very interesting. Anyone has another question? Okay, if no more questions, thank you very much. Congratulations for your work.
Thank you.
We still have some minutes to the next paper. Cassie, are you going to present the paper?
I'm gonna show a video.
Okay. So I think we can move on to the next paper. So for those that just arrived, we are on the second section of vision sensing mapping of LARS. Welcome. The next paper is entitled Internal and External Environment. Sorry,
Valdir. Sorry,
yes.
It's Luis. I forgot to say in the beginning. If you allow me, I want to say something.
Yes, sure.
Okay.
It is with regret that we inform that on the 7th, it passed away Professor José Tenreiro Machado. He is on our program committee this year. Unfortunately, we knew that yesterday from a message that we got from his family answering an email from James, an automatic email. And just to say to everyone, Professor Tenreiro Machado was born in 1957 in Pinhel. He is from Portugal and dedicated a large part of his life to the Porto Higher Institute of Engineering. So he is at the Polytechnic of Porto. He was, sorry, at the Polytechnic of Porto. And just to say the community, I don't know if everyone is knowing about that. We are really very sorry about that. He was with 53, 54 years old now, okay? Sorry interrupting, but I think this is just for his family to know that we liked him very much and we are very sorry about that, okay? Thank you, Valdir.
Thank you, Luis, for sharing this. Our condolences to his family. So the next paper is entitled "A Comparison of Visual SLAM Algorithms, or SLAM2, RTAB map, and SPTAM in an internal and external environments with ROS." So Cassie is going to present, and then later we have questions. Okay.
Yeah, I'll share my screen right now.
Cassie, I think the organization will play the video that you have uploaded. I think it's better, right? Okay.
Right.
Okay, thank you.
Hello everyone, my name is Castilhanto Jesus. I'm Control and Automation Engineering student at the Federal University of Santa Maria, and now I'll be presenting a work titled Comparison. Hello everyone, my name is Castilhanto Jesus. I'm Control and Automation Engineering student at the Federal University of Santa Maria, and now I'll be presenting a work titled Comparison of Visual SLAM Algorithms, more specifically RBSLAN2, HERTAB and SPTAN, in an indoor and outdoor environment with ROS. And in the introduction, I'll be showing the objective of my work and what is the problem that involve the visual Islam. And in the theoretical background, I'll be showing the modules diagram system of the HERTAB map and RBSLAN2, and what is the type of cameras that normally used in these algorithms and the difference among these cameras. It's very important. And the materials, it's basically the software that I used in order to do the simulations on the ROS. And for example, the robot that I used, or the language, the programming language, and so on. The methodology would be basically the methods that allowed me to realize these simulations, like how I get the ground truth for comparing to the accuracy of the visual Islam algorithms that I'm showing here, and the results would be obviously the results that I obtained with the simulations, more specifically the results related the accuracy of the robot trajectory, graph, and so on. And finally, the conclusions were basically my final conclusions of these experiments. There were 4 conclusions, by the way. And I'll start now with a brief introduction and overall what these algorithms are. It's basically to build a map and self-localization at the same time using cameras, obviously, and it can be monocular, stereo, and RGBD cameras, and so on. And the objective here is to compare 3 visual simultaneous localization and mapping algorithms applied to mobile robotics at the ROS. Like I said, RBSLAN2, HERTAB map, and SPTAN. And that's the modules diagram system of the HERTAB map. And there are 3 types of cameras that's more used than these algorithms, and it's basically monocular camera, RGBD camera, and stereo camera. And monocular camera is one simple camera that gives us images, and the RGBD cameras, it's basically the same but with a depth sensor. And finally, stereo camera basically are two monocular cameras separately each other for a certain distance. And how you can send the images for visual odometry module, that's basically estimate the pose with images, and after that send the frame and pose for other module, then add the keyframe to graph, detect loop closure and graph optimization to do the odometry correction and build the map 2D or 3D. In my case was 3D, obviously. And that's the modules diagram system of the RBSLAN2. The RBSLAN2 work with 3 threads working in parallel. There are tracking, local mapping, and loop closing. On the tracking, it's done the image pre-process plus a track local to generate the keyframe. And for the local mapping, it's done the keyframe insertion plus local body adjustment. And in the loop closing is done the loop detection plus loop correction. And finally it's done a map update and full body adjustment and the final of the whole process. And these are the software that I used and the ROS to make the communication of the robot. It's very important. The gazebo to create the simulations of the environment, and the HERVs to visualize the results of the mapping and tracking, the Collab platform to process the data that would be the pose estimate of the visual Islam, and finally the Python and C++ to programming languages. And that's the robot that I built in order to make these simulations, and that robot is named the Robot Differential Drive. He has 2 cameras, more specifically RGBD and the stereo camera. And that's the environments of the simulations. These environments can be found in the gazebo, and an indoor environment is basically a museum, and the black arrow, it's where the robot will do your trajectory. But the question is how I get the ground truth trajectory to compare to the estimate trajectory of the visual Islam. And basically I used the undermath of the robot to get your odometry with you can predict the destiny spot. It's easy to do. And I'll show in this video 4 simulations. I'll get started now. And how you can see, the HERTAB map created a 3D dense mapping, and on the other hand, Orbis 2 created a 3D sparse mapping. We have here HERTAB map, HERGBD, HERTAB map stereo, and Orbis 2 HERGBD and Orbis 2 stereo. And in the first simulations, more specifically HERTAB map HERGBD, and the end of the trajectory, the HERTAB map got trouble because the HERGBD camera is limited due to the short depth detection. Finish. And the results, and finally the results, you can see the left and right HERTAB map HERGBD indoor and HERTAB map stereo indoor, and the trajectory estimate plus ground truth respectively. And one interesting thing, it's you can see in the final of the trajectory, the algorithm got a noise due to the lack of visual information. And over here we have the Orbis 2 HERGBD indoor and Orbis 2 stereo indoor respectively. And over here we have HERTAB map stereo outdoor and Orbis 2 stereo outdoor respectively as well. And the HERTAB map stereo outdoor got the great estimate trajectory, how you can see here. And over here we can see the SPTUM stereo indoor and SPTUM stereo outdoor. And these are the measurements of the trajectory distance, and how you can see the better performance was the Orbis 2 HERGBD indoor. He got more or less 6% of error, and the HERTAB map stereo outdoor he got for about 4% of error. And I got 4 conclusions about my simulations. And my first one, unfortunately the HERGBD camera, more specifically Kinect, cannot provide a trajectory because of the lack of feature and limitation to capture depth for long distance for outdoor environments. And the second one, the HERTAB map stereo, showed a more accurate estimated measurement for outdoor environment. The third one was the Orbis 2 HERGBD showed to be more accurate for indoor environments. And finally the Orbis 2 had the best accuracy in the measure of the trajectory distance. Thank you.
Thank you, Cass. Any questions from the audience? Okay. I have a question. The tests were done in simulation only, or did you implement it in a real robot?
Basically worked out only in virtual environments because of the COVID pandemic. it's got turbo to it.
Okay, and did you implement the virtual environments yourself, or you have you worked with a preset, an environment preset? An environment. Have you built your simulation environment yourself, or have you got the simulation environment from elsewhere, from open source?
I got in Gazebo.
In Gazebo. Okay.
Yes.
Okay. And also the path when comparing all the methodologies, the robot performed the same path in all the methods, or the path changed from one method to the other?
Can you repeat?
Okay, have you teleoperated the robot, or have you pre-record a path and the same path was taken each for every method?
I used the tools of the ROS called bag ROS, because it's basically you build your own data sets and you record everything and your simulation if you want, for example.
Okay, we have a question from Luis Gonçalves. How do you?
If I can make it here, it's okay.
Yes, sure.
Okay, Cassie, I'm just asking if you have had some experience in the past about this thing of coming from simulation to real. I don't know. I think when we are in robotics, everyone wants to see real robots. And how do you see this? And do you think it's going to work, or how the thing is worked are doing today in this line? So, several times ago, I don't go to this line to see how is simulation or real.
Design the robot?
No, your work you did in simulation. So do you think it's going to work in the real robot when you? That's what I asked. Or what kind of problem do you think you have?
Oh yeah. Basically, I got no problem in my simulations. Just the ROS make it easy to do the simulations. I don't know.
I don't know. Okay. Of course, there are some challenges from changing from simulation to real experiments.
Can I ask something as well?
Yes, sure.
Yeah, I'm just curious about because Netic it's not a robotic tool, but still it's very handy, and it's not being produced anymore. It's a problem to us that use it. But I'm just curious about how far is the threshold? I mean, how big is the room, or are the things need to be far away from the robot so the Kinetic cannot estimate a good map? Have you do you have any tests, or do you know which distance is this? Because you said that the sensor is not good because of the distance, but okay.
Depending what your camera that you use in this moment, for example, in outdoor environment, it's more better to use stereo camera, and indoor environment it's got more accuracy and indoor environment, and that's was the difference that I got in these simulations.
Okay, thanks.
Okay, Dunfrey, a quick question.
Yeah, I keep thinking about the longer road can accumulate errors, and this can make difficult to reconstruct the road, right? And about your test, is there any perspective of training on a larger route that ones you have in which you can accumulate a lot of errors?
Yes. Tend accumulated errors and along over time, and but I just did one path, and basically that's
how long?
it. How long? I'm not sure, but 10 meters.
10 meters. Okay.
I think yes. And indoor environment at least.
Okay. Humphrey, thank you very much for your presentation. Thank you all for all the questions. We are moving on to the next paper. The next paper is a visual inspection proposal to identify corrosion levels in marine vessels using a deep neural network from Luciane Soares, Silvia Botelho, Ricardo Rodrigues, and Paulo Drills. Who is going to present the paper? Luciane?
Hi.
Okay, thank you. Are you going to play the video or make a live?
I prefer the video.
Okay.
The connection is stable here.
Okay, thank you. Organization. The organization could play the video, please.
Hello everyone, my name is Luciane. I will present the article, A Visual Inspection Proposal to Identify Corrosion Levels in Marine Vessels Using a Deep Neural Network. Introduction. Brazil produces an average of 3.2 million barrels of oil per day. Is the 19th largest producer in the world, due to discoveries offshore for such reserves. It is estimated that Brazilian production could reach around 5 million barrels per day. Thus, the use of platforms is increasingly common and concerns about their integrity and extra increase. Ships, platforms, and float vessels are exposed to environment conditions that can cause external physical defects such as cracking, corrosion, and biological incrustation on the surface ship hull. Periodic inspection of floating units is necessary to verify the structural integrity and surface of the ship hull. Is important to improve the operational safety and efficiency of ships. Traditionally, inspection of underwater metallic structures is realized through of visual observations by human divers. However, this type of activity is unhealthy, laborious, and costly for women. Therefore, the practical efficiency and quality of inspection results are limited. Thus, remotely operated boats are an alternative to the underwater inspection task. The ocean is an environment composed of suspended particles. These particles cause some distortions in the propagation of light in the water. Thus, underwater images have reduced visual quality, differentiated type of coloration, low contrast, and no uniform light, making it difficult in analyzing the details of captured images. A term often used for this phenomenon that degraded images is turbidity. Proposal. This article proposes to use a CNN to identify for corrosion levels: no corrosion, low, medium, and high new underwater images, and the construction of a synthetic dataset with application of the turbidity effect. First three form the data provided in the article by Bastian. The reproduction of the custom CNN network of the article was first made with some changes, which will be demonstrated, but used for training the test dataset with 39,600 images provided by the author. Second approach was performed on the dataset provided to add the turbidity effect to the images, leading to these images characteristics of underwater image. The dataset original used for the training and validation of the experiment consists of 39,600 images of pipeline with different corrosion levels, 9,900 images of each corrosion level. 30% of the dataset is used for validation. Dataset with turbidity effect. For this experiment, it is necessary that the images contain effects of underwater images. For this, the degradation of the available dataset was performed through a degradation function as presented in the article by Mello. The degradation function allows to simulate a degradation generating turbidity in the images by changing the gamma variable in the image. Figure 1 demonstrates the original dataset at the upper and the dataset with turbidity effect at the lower. The test dataset public images were acquired from the internet. It is composed of 40 images, 10 images of each corrosion level. This dataset was also submitted to the degradation algorithm. The figure 2 shows some examples of the images contained in the test dataset. Network architecture. The proposed neural network model is based on network present in Blossom, but dropout layers are added between the convolutional layers to reduce overfitting. Custom CNN network uses convolutional layers and fully connected layers, thus fewer number of parameters compared to ZFnet and VGG, and therefore can be trained using a new dataset. The parameter set for networking training: number of epochs 30, batch size 100, learning rate 0.001, and momentum 0.9. The training was carried out on Google Colab in the free version. Original dataset results. The results of 40 images, 10 images of each class, with corroded areas without the turbidity effect. The image labels of this dataset were kept the same as the base article. Class 0 for high corrosion, Class 1 for low corrosion, Class 2 medium, and Class 3 without corrosion. Of the 10 images of Class 0, all were correctly classified. From Class 1, 90 images were classified in the correct class. Class 2 classified 90 images as correct. Finally, Class 3 had 7 images classified correctly. In the figure 3, the confusion matrix with the results obtained using the dataset no degradation effect. It can be seen the results obtained were satisfactory, as the confusion matrix present 87.5% accuracy. The graded dataset results. the dataset with the graded images. The classes were labeled as Class 0 for images without corrosion, Class 1 for low corrosion, Class 2 for medium corrosion, and Class 3 for high corrosion. The confusion matrix showed 92%, as can be seen in Figure 4. Classes 2 and 3, all images classified correctly. Class 1 had 9 images classified as correct and 1 image classified as Class 0. Class 0 images without corrosion presented 8 images as Class 0, 1 image as Class 1, and 1 image as Class 2. Conclusion. The article proposed the construction of a synthetic dataset with underwater image effects, simulated turbidity, through a function of degradation and alteration of the gamma variable of the images. After a CNN network based on the architecture presented in the work of Bastian was built to identify levels of corrosion in underwater images. The results were analyzed using the confusion matrix, which showed 92% accuracy for the synthetic underwater images of the test dataset. It is considered a satisfactory result for the initial work. The next steps go to augment the test dataset, make a real dataset for underwater images, and embed the proposed corrosion level identification algorithm with a single board computer for use in a ROV in the future. Thank you.
Thank you, Luciane. Any questions from the audience? From YouTube? No questions. I have a quick question. The turbidity data set, have you considered using a generative adversarial network to generate, or I don't know if it is the focus of this paper, the construction of data set. Could you comment on how you generate the turbidity effect? I think no, I think she is she still here? I think she's not here anymore. I don't
Luciane?
she's not on the list. Probably the connection. She mentioned that the connection, that her connection was not good, so probably she couldn't.
Is Drills in here? I think this work is from Forgy. Someone from Forgy.
No, I don't think. Okay, I think we can write the authors. Okay, from to ask questions, but interesting work. Let's move to the last paper of this section. It's localization using OpenStreetMap landmarks from Maximilian Kunz. Maximilian, are you?
Yes, can you hear me?
Yes.
Nice.
Are you going to present live, or are you
yes, I would like to, if that's okay.
Okay, yeah, sure. Can you share your screen?
Yes, let me just see if that's possible, and also if I can. No. So you should see me. Am I allowed to share it? Yes,
Yeah,
I think
you
so.
should, yes.
Can you see it?
Yes, it's not, yeah. Now it's great. Thank you.
Okay, hello from Germany here. My name is Maximilian Kunz. I'm a master student at the Technische Universität Kaiserslautern, and I'm presenting to you my guided research with the topic localization using OpenStreetMap landmarks. So here is the table of contents. First, the basic idea, what I had in mind to solve the problems of localization using OpenStreetMap. Then the detection part, because I did all my approaches in the simulation. Then the algorithm I created, some experiments, and the final part will be about future work and summary. So here, this displays the basic idea, because my algorithm or my idea was inspired by the way how humans localize them, because we don't use GPS coordinates, we don't have such sensors in ourselves. We normally use landmarks. So we have, for example, internal representation for the path we take every day to work, or for other paths, or we use an actual map, and then we compare these this data, this map that we have internally or on our smartphone or wherever, to landmarks. So for example, huge buildings, churches, for example, in cities, or similar objects. And here you can see the basic principle. We have a local, by the way, can you see my cursor?
Yes.
Yes.
Okay. So here we have a local view of our current scene. So this, you can imagine it as a camera, and the camera detects, or the camera looks at a scene, and it can detect objects, for example, a bench or fire hydrants or entrances. And then we have here our global view. This is, in my case, the OpenStreetMap data. So for those of you who don't know OpenStreetMap, it's an open source project for basically mapping the whole world. And the data is, the raw data can be accessed by anyone and is free, and you can use it for everything you like to do. So we have our global view here and our local view. And what we want to have is our landmark matching, because we know where we are in comparison to our local objects. And when we figure out where these local objects are in the global view, then we know where we are. So this is the basic idea. So what I did was I used OpenStreetMap, as I said before, and for my case, I used unconnected OpenStreetMap nodes. These are, as the name says, suggests nodes which are unconnected, so they're no part of edges or of paths. These are, for example, this is the campus of the Technische Universität Kaiserslautern. Here is the most important part. It's in front of the Mensa. And here you can see some examples. These are benches or entrances and artworks. And this is an enlarged attributes table, because when they're in OpenStreetMap, there are several tags or specifiers for identifying single objects. And here I only use what I call primary tags. The primary tags are those pairs of key and value which identify the object the most, because when you look at the example, you can identify an object, or rather the geometry of an object, better with the knowledge that it's a bench rather than the color is white or it's made out of wood. So I use only the primary tags, and the additional tags, they can later be used for more accurate identification. Because right now, for me, every bench is just a bench. The color is not important, and the material is not important. So now we have our global view. These are the OpenStreetMap nodes, and the next part will be about the detection. So the detection was, as I said before, completely done in simulation. In our work group, we use Unreal Engine, the gaming engine, Unreal Engine, for our simulations. And there I used an Unreal, what is it called, an Unreal Engine post process, and custom stencil and custom depth buffers. So this is just a short visualization. Here I have a simple scene in the simulation. You can see there is a brick wall here in the front, and the back there's another wall. And I have these two squares I want to detect. So these, you can imagine it as my OpenStreetMap objects. So for example, the one is a bench, the other one is, fire hydrant. And what I do in the simulations, I I give these objects I want to detect specific values. It's called a custom stencil value. And in Unreal Engine, for every custom stencil value that is bigger than 0, it's getting rendered in a different pipeline. So for the normal view, we have our scene, and we have illumination, we have shadows, we have the base color, and so on. But this one is rendered in a specific pipeline, and it's only rendering the custom stencil values. So this is what you can see here in the next image. I hope you can see the contrasts are good enough. So you should see this white square. So this is rendered in a different pipeline. So, and what I'm also doing is I use this pipeline to figure out if an object is behind another one. So this is the occlusion of objects. You might be able to see it here. And this is the visualization of the resulting image. You can see that these yellow parts is the part where the object is not occluded, and the red channel here, so it's a RGB channel image, and the red channel shows occlusion. You can see that this object is here occluded, and I'm using this resulting image for my detection. So what I get from the simulation is a bounding box of the objects, and of course, the global and local distance, because I know where my camera sensor are, and in the simulation, I perfectly know the distance between every object, basically everything. Then I get the primary tag. This one I get from the OpenStreetMap database, because in the simulation, I use data from OpenStreetMap and to create these objects. Then I know the primary tag and also the other tags. And I've also added a value confidence, which I have not used in this, I think in these experiments, but it is basically an estimation of how likely it is that this object can be detected. So this is, for example, when there is an important object close to a wall or behind bushes, and it's very unlikely that it's ever going to be detected, then this value is pretty low. So we have our local view now and our global view. The next part is the algorithm. This is part of several subparts. The first one is to find a match, because what I have now, I have my global OpenStreetMap map, and then I have a local view. I know I have 4 objects around there, and I have to find the first match between the objects, because I don't want to compare all objects, all detected objects to all possible objects every time. So what I do now is visualized here. I have on the left again my local view, and on the right is the extract of the, let's say, the OpenStreetMap view. And the similar shapes reflect the primary tag. So for example, a triangle has, in this case, a primary tag triangle. So this is the only thing I'm differentiating them. So the first match is found by just comparing one object I have detected to every other object, as you can see here. And this takes a lot of time. So I only want to do this as few times as possible. And this is the first step. So I found, now I have found a first match. What I want to do now is to update my possible matches, because in the previous step, my possible matches were basically all the objects, or if I had a previous step, a smaller area. And this one is then the next step. So here I have these triangles is the objects I have matched. So I know that these one, they match. And what I do now is I update my possible match box with the double the biggest extent of my of the local extent of my bounding box, what I have detected, and I center it around the match I have, because I have no idea how anything is rotated. I just know I have found one match. So the next part is then to look at the neighborhood of the bounding box. So these are these objects. I want to compare them to those. And here I have 2 measurements. First, I can, again, only consider the tags. So I look at my detected box and my newly neighborhood, and I just compare the tags. Or I can also use the distance for comparison. This is what you can see here. I know the distance from my local view. And then I can calculate the circular shape in which the objects can be. So this is all with some thresholds. So I think I used always around 20 or 30 centimeters, which is then still equal. So what I can then do is I update the matchbox, my detected area, if the neighborhood was successful or below a certain, above a certain threshold. And then I can then, since I have now my bounding box, which should be as closely matched as my local detection, I can compare the bounding boxes. Here again, I have 3 metrics. I can compare the primary tags again, only the primary tags. Then the bounding box extends, since I now have my correct or as close as possible, my bounding box now, and I can also compare the local signed distances. So this is what you hopefully can see here. On the left again, compare every detected object with every matched or possible object. And in the middle, you can see the bounding box extends, and on the right, this is the local distance. Because now I have also orientation of the bounding box. So here we have our local view then, the global view, and now our matching. So we are done. Now to the experiments. First, so as I said before, it was all done in simulation because when I started my guided research, there were no detectors in our work group for for these objects. So I had to do it all in simulation. So my first experiment, I used in the simulation on our campus the perfect location of my vehicle and my estimated location. And I said when the estimated location is within 3 meters of my perfect location, I say, okay, this matches. And for similarity, I used the neighborhood similarity by tags and distance, and the bounding box similarity tag, extend, local distance. So basically the most measurements I can use. And here you can see the part of the campus I used. So the pink volumes are where the estimation and the real location where the difference were smaller than 3 meters. So as you can see here, it's mainly, by the way, the building in front on top is the Mensa. So this is what I showed you before. And if you can remember, there were a lot of objects in front, so basically a lot of benches in front of the Mensa. And this was very important for detection because, for example, on the path between buildings, there's usually not many objects. There are maybe a few benches, but it's basically only a path and grass and some trees, but they are not inside the OpenStreetMap database. So if there's no landmarks, I can't do landmark matching. So this is what was expected, and it also shows here in the experiments. The second experiment was with a smaller radius of acceptable distance. So this is just 1.5 meter, and I also only used neighborhood similarity and no bounding box similarity. It's the second experiment. You can see that it's again close to the Mensa area here. There are a few matches, and on the same path, it's basically more or less a clustering of this is the first experiment, because here again, this one is a big area, then here is the area, and this one where the detection was pretty good. So here you can see that this is basically the center of these clusters. Now I come to the future work, which I want to do probably in my master thesis. So again, as I said, when we don't have landmarks, we can't use landmarks matching. So I want to use more information from OpenStreetMap, like the paths or outlines of buildings or surface data. Then I also want to use this approach to verify OpenStreetMap data or check OpenStreetMap data and maybe also add new data. And the next important part would be to combine it with other sensors like IMU or GNSS sensors, and to test it with a real detector in reality, because in simulation it's very different than reality. And in the simulation part, I want also to improve my detector. Now the summary, what I did, so summing up everything, I created an image-based detector for objects in the simulation. For specific objects I can select. Then in our work group, I created the first approach for a landmark matching based on OpenStreetMap data. And the main result basically is that I need more landmarks for a robust landmark matching. So thanks for your attention. If you have any questions, feel free to ask.
Thank you, Maximilian. Eduardo, do you have a question?
Hi. Do you hear me?
Yes.
Okay. I am Eduardo Todo from Federal University of Paraná. Nice work. I like it a lot. The idea of discrete landmarks is very interesting and attractive. Do you consider taking into account the spatial organization of the landmarks, also not just the distance between the landmarks?
What do you mean with special organization? You mean like
for
groups,
example,
groups of
not
objects?
just the distance to the landmarks, but also the bearing, because as you move, this organization, the view of the landmarks that you have changes. How do you compare it?
No, in my approach, I did not take this into consideration. What I did for simplification, I basically try to solve the wake up situation where I am just waking up somewhere and I see one scene and I try to find out where I am in the world. So
it's like having a bag of landmarks. In this view, I have these 3 or 4 things that I can see, something like that.
Yeah, it's just one. It's basically just for one image, more or less. I did not consider several image in this approach, but it would also, yeah, this is also a problem for different views. It's also what I this is what I did in the simulation, because it would be in totally another work to detect objects from different angles.
Yeah. Okay, but great. Thank you very much.
Thank you for your question. Julio, just a quick question, just so that we
okay.
behind the schedule.
Yeah. Very nice work. I was just curious, because why are you trying to solve the location problem for outdoors, since this approach is definitely, at least it seems for me, that it's better to indoors. I mean, indoors you have lots of objects, and if you have the position of those standard objects, you can maybe not easily, but you can maybe have more or at least better results for indoor buildings. I mean, you can just track your robot inside of Mensa by using this approach. It seems for me that it's more suitable. Have you tried it?
No, so it's certainly very good for internal use, but for some parts I didn't use it, because in our work group we only do outdoor robotics. We have not really that many indoor robots, and another problem is that OpenStreetMap data is only available for outdoor, so we don't have indoor options, but it could also be used for indoor scenarios. But again, we mainly do outdoor robotics.
Yeah, you could try to start a kind of not OpenStreet, but open maps for your university. Maybe. Yeah, maybe. Yeah, thanks.
Thank you. Thank you, Max. Congratulations for your work. We are closing now the first session of the day, Vision Sensing and Mapping. Now I invite Marcus Maximo from Aeronautic Technology Institute he will be the chair of the next session, Robot Soccer. Thank you all for attending this session.
Thank you, Valdir, for being here. I'm Luis, I'm not Massimo, he will be here just soon. Just to invite you for our cultural program tonight. And in this cultural program, we are going to announce the best papers of LARS and RRE 2021. And also those that we have selected for being submitted to the Journal of Intelligent and Robotic Systems. It will start at 7 p.m. Okay, thank you.
Hello, can I start?
Sure.
I believe, yeah.
Okay. So I'm Professor Marcos Massimo from Aeronautics Institute of Technology. I'm going to be the chair of the technical session about robot soccer. And the first paper will be geometry analysis and force simulation of a kicker system's flat solenoid to robots for the small size league category. The paper will be presented by Danilo do Nascimento Santos from Federal University of Pernambuco. So is Danilo here?
Yes. Hello, Carl. Hello, Marcos. Hello, everyone.
Hello, Danilo. Are you going to present live or do you prefer to present with the video?
Could you present my video, please?
Okay, so I think the host here will present the video. I think it's Julio. Okay.
Hello, I'm Daniel Santos. I'm a student of Automation and Control Engineering at the Federal University of Pernambuco. Me and the other authors of this work are members of the Mechatronics Robotics team. And I'm here to present the study we made for our robots. Geometry analysis and force simulation of a kicker system's flat solenoid to robots for the RoboCup small size league category. But first, let me explain a little bit of the RoboCup competition and the small size league category. The RoboCup competition is a robotic competition that has the ultimate goal to make a team of autonomous robots that not only could compete but win against the best team of human soccer players in the world. And the small size league category is one of the categories of this competition of soccer. It has the limits of the size and kicking speed and others. And just like real life soccer, the kick is a really important part of the game of soccer playing robots, since we need to not only pass the ball, but to score goals. The kick is centered around a solenoid, a device comprised of a coil of wire, the housing, and a movable plunger. When an electrical current is introduced, a magnetic field forms around the coil, which draws the plunger in. This movement is what makes the plunger move and kick the ball. Here, I can show one of our tests of our kick system. We use a solenoid Solatec Series D. To make more clear how the kick works. As you can see, when the current passes the coils, the kick happens. Our old project already had a working kicking system, but we wanted to improve it even further, since it was limited by one type of kick, a flat kick, which is the kick that can only push the ball forward. We wanted another type of kick, which is the ship kick, that can not only make the ball go forward, but upwards too, in a parabolic trajectory. And to make this happen, we need two solenoids inside the robot. When we tried to use the solenoid Solatec Series D, it proved to be not possible to fit everything inside the robot. So, to solve this, we wanted to try and develop our own solenoid. We researched in many projects to develop our own solenoid. Some research and studies that helped us for Gears study on Helitan's coil gun focused on the middle-sized league. Helitan's coil gun itself is the solenoid that we use to kick the ball. It was primarily focused on middle-sized league, but it was really useful since it had tips to optimize your solenoid development, and it had some simulation software that we actually used, like FAN. And other things that compete in the small size league were really useful, like ER Force and RoboIM, since both of their projects use two solenoids for the same function that we want. One for the forward kick and other for the ship kick. Now, we start to develop our own solenoid, starting with the mechanical project. The biggest inspiration for our solenoid was RoboIM's ship kick solenoid, since it had a flat geometrical shape that could fix our problem of fitting two solenoids inside the robot. The only difference between both solenoids is that ours use a mixed plunger made of aluminum on the heating point of the solenoid of the plunger and magnetic steel and a ferromagnetic steel, which is steel 1010. The housing also is steel 1010. So take the limitation of the robot, we can achieve the basic components of the solenoid, such as number of turns and type of wire. We use the wire 24 AWG for the copper wire. We had a free space of 84 millimeters for winding. So to this type of wire is resulting in 164 turns. And we had also free space of width of 2.9 millimeters, resulting in 4 layers of 164 turns. In total, solenoid resulting in 656 turns. To obtain the current we need for the force simulations, we simulated our old circuit first, which is a discharge circuit connected with the old solenoid Celatec Series D. But this time, the values of inductance is the value of our own solenoid. This inductance was obtained using fan. So we simulated the discharge of two 2200 microfarad capacitors parallel on our inductance, and it resulted in current peak of 92 amperes. Now we can simulate the force. To validate our solenoid, the solenoid will need to kick the ball with sufficient force to make it reach the ball speed limit of the competition. In the case of the small size league category, it would be 6.5 meters per second. And to obtain the speed, we made an estimation. Since the plunger and the ball will travel together when the kick happens, the speed of the ball will be the same as the plunger. So we need to just obtain the speed of the plunger. This can be achieved if we have the force. With the force, we can calculate the speed. And the force itself can be obtained by the usage of some electromagnetic simulations, like fan, that can make the magnetic analysis of the flux density and calculate the force in a region, which in our case is the plunger, by the method of stress tension analysis. Using the Python library, which is a Python library that can interact with fan, we further improve our work simulation. Now, I'm going to explain how the Python script works. It will simulate a copied fan file and will store the position, the force in this position by the stress tension analysis, and the speed calculated with the force inside the Python script. And it will check if the plunger has reached the end of its movement, the end of the kicking movement. If it has not, it will increase the position of the plunger and will simulate again until it reaches the final position, which is 31 millimeters. If it has reached the final position, it will return the table with all the values of speed and force in each position. To validate our project even further, we used Discovery AIM, which is a three-dimensional simulation software that could, just like fan, simulate the electromagnetic influence on the solenoid and plunger, resulting the force of the plunger in a determined position. And then we have the results. The first analysis we made was to define the length of the ferromagnetic part of the plunger and how it would influence the force, since it is part that is responsible to be influenced by the magnetic field created around the coil. In order to do simulations, it resulted that the increase of the ferromagnetic part of the plunger would also increase the overall force of the kick, but with diminishing returns as the plungers grow. And we also found that, in effect, when the plunger, or at least the ferromagnetic part of the plunger, totals into the coil, a force will be experienced on the contrary of the kick. So we need to make a plunger that will never totally into the coil, which is a plunger with at least 70 millimeters or more. For the final design of our solenoid, we choose the length of 8 millimeters for the back part of the plunger, and then we simulated the kicking movement and the force experienced by the plunger. And when using fan, the force experienced by the plunger would have a peak of 170 newtons at the end of the percourse. This would mean a speed of 5.34 meters per second, which is lower than the ball speed limit of the competition. But when we simulated it with ANSYS, we had a higher force of 280 newtons, which would mean a speed of 7 meters per second. This result was higher than fans, most likely because of the more consideration in the 3D design, since we have more ferromagnetic parts like the housing that help to direct the flux, increase the flux, increase the force. So we need to lower the speed now. We can lower the speed by lowering the current experienced on the coils. This could be achieved by changing the capacitors. In the end, we could validate the project of our solenoid, with the usage of both software proving really useful, FAN and ANSYS. FAN for the fresh simulations and the Python implementation that could make your project easier, and ANSYS for the precise control of your model that could achieve a higher force when compared to FAN. I'm really grateful for your attention. If you have any doubts or further questions about our work, you can contact us with the emails on the screen. Thank you.
Thank you for your presentation, Danilo. I think we have time for 1 or 2 questions. So we have no questions from YouTube. Does anyone want to make some question? So
yes,
I
have a question.
Okay, go on.
So Danilo, thank you for your work. It's really great.
Thank you.
Did you perform some tests with different numbers of turns in the solenoid wire or different diameters? Because you used AWG24, I think. Did you consider changing the diameter of the wire or the number of turns in this work?
Yes, we did. We changed the diameters. We had some tests, but we focused on AWG24 WG because it was the same as used as before. But we did some tests with another type of coils of wires.
Okay, thanks.
Thank you.
We have another question from Leonardo in the chat. He's asking, what future applications do you imagine with your paper? Do you think about some kind of application in industry?
Wait a minute. No, it's more centered around the competition of football competition and Rebel Cup. But it can be used for any type of solenoid, I think, because yes, it's the reluctance coil gun solenoid, but it can be used to any type of solenoids which have this construction, because we calculate the force and yes, we enter the speed, but if you have a project and you need the force or the speed, if it's not on the RoboCup, but to another application, you can use our project as a study.
Okay, Leonardo has another question. He's asking if during the development, did you consider which are the largest source of error in your results?
Okay, that's a good question. We could lose electric energy. The current could generate heat on the wire, so this would lose force in the end, and we need to project the return of the solenoid, which could be achieved by using springs. This construction could lower the overall force of the project too. But we need a solenoid. We want to make a solenoid that could not only be for the ship kick, for the upper kick, but a solenoid to the forward kick. So if we lose some speed in the ship kick, which is our primary focus, I think it will not be so bad, since it's not like for the kick, if you know what I mean. It's just we need just to pass the ball for upwards.
I see. I have a question too. So in your simulations, I think that you are trying to achieve some kind of maximum speed, but I think that in robot soccer, in small size league, you also want to control the speed of the kick to make some kind of pass, for example. So yes. Did you consider something like that during your simulations or during your work?
Yeah, we can control the speed by on our solenoid. We just consider the overall maximum speed of the solenoid. I think we could change, just like I said, with the capacitor on this. We could. I don't know if this could be achieved by the rest of the project, like the control system and overall. But for our solenoid, the electrical design, we could only control the maximum speed.
I see.
And change with the capacitors.
Okay, thank you very much. Congratulations for your presentation.
Thank you.
So I'm going to the next presentation now. Because of the time, the next presentation will be a minimalist open source behavior tree framework in C++. It will be presented by Gustavo Silva from Aeronautical Institute of Technology. So Gustavo, do you want to present it live or do you prefer to present with the video?
I prefer to use my video, please.
Okay. So Julio, can you please share the video? Okay, thank you.
Hello, I'm Gustavo Silva. I'm an undergraduate student at Aeronautics Institute of Technology. And on behalf of Marcos Máximo and Lourenço Pereira, I will present a minimalist open source behavior tree framework in C++. So let's start. Our presentation is divided in 4 parts: introduction, theoretical background, results, and conclusion. So starting with introduction. First, about our team. Our team is called Androids. It is a robotics team in São José dos Campos at Aeronautics Institute of Technology. We participate in robotics competition and related areas since 2005, and we have won many awards since then. For example, in LARC, we have been consistently placed in the first place of the competition. So we have lots of experience in developing robotics applications. Our team has many categories, for example, humanoid, very small size, and in all of these categories, a very important aspect is the decision making. So all of our categories use or plan to use behavior tree as the main agent architecture, but we do not have a formal structure to organize these behaviors. So that's the purpose of this project: develop this framework to organize behaviors. So we contribute by developing a minimalist open source behavior tree framework First, it was developed for our internal purposes, but then we found out that it could be used by pretty much anyone, since it was very simple to use and to integrate. So we decided to share it in LARS. So that's the motivation behind this project. Here I talk about some related words. For example, in the video game industry, behavior trees are very important to model AI of video games. So most of game engines such as Unity and Unreal, they provide structures for behavior modeling, and many of them are based in behavior trees. In robotics, we have a ROS-based library. ROS is a very popular middleware toolkit for robotics, and ROS Behavior Tree provides a behavior tree structure for ROS. Here we make a comparison about our work and ROS Behavior Tree. So, in terms of features, it is important to emphasize that our framework is a micro framework, meaning it's minimalist. So we only provide the basic structures and functions to form a behavior tree. We don't provide anything else. ROS behavior tree, on the other hand, is a very more complete framework. It provides a graphical interface, Blackboard debug features, etc. So in terms of features, ROS behavior tree is more complete because our purpose is to make a minimalist behavior tree framework, a micro framework. But in terms of simplicity, our work is implemented in pure C++, so we don't require any dependencies, meaning it is very easy to integrate in any project since it does not use any other dependencies. And the implementation is intuitive and quick. You can make a behavior tree very quickly using our framework. And ROS behavior tree, since it depends on ROS, it is engineered for ROS, it requires many dependencies of ROS. And the interface of this library must be compatible with ROS. So we think our work is very more simple, which comes at the cost of having less features. And in terms of efficiency, our work is very lightweight. Each node takes only a few bytes of memory, and the tree processes very fast. So any implementation of our tree is not bottlenecked by the structure. It is very efficient. So you think it is very lightweight, very efficient. And ROS behavior tree, it is also very efficient, but since it has other features and dependencies, they may affect the performance. But it is very efficient, nonetheless. So in terms of features, we think our work has less features, but we provide a more simple way to form a behavior tree. So let's proceed. Now we make a theoretical background on behavior trees, how they work. So a behavior tree is an extensible, high modularized tree structure of hierarchical nodes, which controls the decision and execution flow of a certain agent. This agent can be an enemy from a shooting game, it can be a robot, any agent. So it is extensible because you can always add more, and modularized because everything is modular. Each node, which is this atom of the its element of the tree, it has a function, and it is hierarchical because each node has a parent. For example, this sequence here is child of selector, for example. And each of its nodes, it can return an execution status, success or failure. And based on this execution status, the tree must decide how to execute the children. For example, in this piece here of sequence inverter, we check if the enemy has cover. If it has, we return success. So inverted, it will invert the result. So it will return failure. So it will not shoot at the enemy because the enemy has cover. But if the enemy has not cover, so we shoot at the enemy. So that's the idea behind the behavior tree. So talking about nodes, which are these elements of the tree, we have three kinds of nodes in a behavior tree. We have leaves. Leaves does not have any children, and they are responsible to interact with the agent, executing an action or checking a condition. So enemy has covered is an example of a condition. Shoot at enemy is an example of action. Composite has two or more children. It decides which of its children should be executed and then process the results. Common composites are selector, which is listed here, and sequence, which is also here. And decorator, it has exactly one child, and it decides how its child should be executed and how to process its execution status. So, common decorators are repeater, inverter, and force. For example, here we have an inverter, which is a decorator in this example. So about our results, implementation follows this class diagram. First, for the nodes, we have this free node. It is the base node for all nodes that are implemented. It is an abstract class. So it has a name argument and a parent due to hierarchical feature. And it has the enter and executed methods of a behavior tree. And see that leaves, composites, and decorators, they all are inherited from tree node. So leaf node, it is equivalent to tree node, but we renamed it just for notation purposes because it makes more sense for the user to implement from leaf node instead of tree node. And it does not have any children. So composite node, it inherits from the tree node, but it has a vector of three nodes, pointers. So it will point to many other nodes. Due to inheritance, children may be leaves, decorators, or other composites. So this tree is not. So the children are not restricted to leaves. They can be composites or decorators. And in our implementation, sequence and selector are already implemented, so you can already use it. Decorator, it also inherits from tree node. It has a single pointer to its child. And this child, again, since it is a tree node, it can be either a leaf node, a composite node, or a decorator. And we have implemented some decorators, repeater, retry, force, and inverter that are available for use. And for that tree, we have two classes. First, behavior tree. It represents a behavior tree itself. A tree has a root, only one root. And the update method executes the tree from the root, and it returns the execution status. And the behavior tree builder, it is an auxiliary class to quickly build behavior trees. It is built with a recursive algorithm with these methods, leaf, composite, decorator, and end. And the build returns the behavior tree object. So it is a builder. In the paper, we show more details on how it works. But basically, it is an auxiliary class to build behavior trees. Here, we make a simulation of a behavior using Python as a simulation. We make an API with C++ and send it to Python. So we have an agent here, a robot, a cleaning robot. It will move forward, move in spiral. If it collides, it must go back and rotate. So let's see. So it is moving forward, following the sequence. Now it is moving in spiral. Oh, but it hit the wall. So it go back, rotate. Now it is moving forward and spiral. And so like that. So concluding, we'd like to thank our sponsors, Altium, Scenic, Intel, ItaX, MathWorks, Messenger, Micropress, Polymode, Rapid, SolidWorks, STM Microelectronics, Wildlife Studios, and Virtual Pixels for supporting our team and this project. And that's it. Thank you for watching. I'm available for any questions about the library, and thank you very much.
Thank you for your presentation, Gustavo. Congratulations. Do we have any questions on YouTube? So, okay, so if there is any question, I prefer not to make questions about this work since I'm one of the co-authors, but I will make some questions. So the first one is, how do you compare this kind of techniques that use some kind of heuristics against other techniques like machine learning, which is the hype currently in artificial intelligence in the domain of robot soccer?
Well, machine learning is a very recent approach to decision making, and while it looks very promising, we think that behavior trees are very much robust for their purpose. Machine learning can be very promising, but it is not always reliable. So when we need a more solid structure, that's why it's so important to have structures like behavior trees, because you know exactly what's going on.
Thank you. And why did you choose C++ for the implementation?
Well, we use it first because it is the user language by our team, Androids, and as it was explained, we developed this work for our category. But C++ has many features. It is very fast, and it has very lots of useful features like templates and an allocation of memory, so they can be very useful for this kind of works when you need speed for real-time applications.
Thank you. I think Julio is with his hand up.
Oh yeah.
Okay, go on. Sorry.
How do you compare to other, because it really seems, I don't know if this is the point, but it really seems like an AI builder. I know that you are building it through code, which is not that helpful. I mean, it's not that helpful to see the things, how things are going, but for you it works because you are the developer of the library. But you can easily, or at least start to think as a AI builder, because you are just building the AI of the robots. And if you are going in this direction, how do you compare to other AI builders? Because it's in the essence, it's the same. You are just building the AI of the robots. If you have another tool to build AI, you can just compare to it. Have you tried in this approach, in this direction?
Well, we think it more as a structure modeling, because the behavior themselves will be user implemented. For example, the leaf nodes, they must be implemented by the user. So we provide the structure, the control of the behaviors, but the behaviors themselves must be implemented by the user. So in that kind of way, I don't think it's exactly an AI builder.
Okay. Because even the leaves, you can just use like block programming or even high level programming on the leaves, and then your tree is just like another high level language that is describing the AI, and you can just generalize. I think it's a very nice start, but maybe you can just extend it to maybe a master thesis or something like that, because it really is interesting, and the even in the direction of other type of AI, like Professor told you, ask you about the machine learning and stuff. Those AI are also aiming towards the AI building, because it's interesting, because it's easier for people to use. So just suggestion. Thanks.
Thank you. Thank you very much for your suggestion, and we will think about it. We think it's very important to, since this structure is very important, since it is very useful on the video game industry and it's very robust. So yeah, this can be very promising. Thank you for your suggestion.
Okay, thank you, Gustavo. Congratulations again. And we are going to go to the next work since we don't have time. So the next presentation is Mechanical and Dynamic Analysis for Design and Development of a RoboCup SSL Dribbling Mechanism. It will be presented by Victor Araújo from Federal University of Pernambuco.
Yes, hello. I'd like to play the video, please.
Okay, so Julio, can you please share the video?
Welcome to my presentation. Hello everyone, welcome to my presentation. My name is Victor. I'm a PhD candidate in computer science at Centro de Informática, Universidade Federal de Pernambuco. I'm with Ed Gleison Silva, João Guilherme Monteiro, Rebeca Souza, Cecília Silva, Pedro Henrique Santana, and Edna Barros, and we are here to present our work, Mechanical and Dynamic Analysis for Design and Development of a RoboCup SSL Dribbling Mechanism. Dribbling is a common skill among robot soccer categories such as RoboCup, Junior Soccer, Middle-Size League, and Small-Size League. The dribbling mechanism is a system commonly positioned at the robot's front and has a motor, a contact system, and dumping system that tries to keep the ball under control. During the Latin American Robotics Competition in 2019, our SSL team struggled in receiving a pass, as the robot's dribbler was unable to absorb the impact of the ball and were also unable to perform complex plays. With that in mind, this work aims to design and develop a kinematic and dynamic analysis method for a dribbling mechanism of a robot under the SSL rules. The main problems we tried to solve were the ball reception at high speeds and the ability to move around without losing control of the ball. Our main contributions are an analysis of the dynamic behavior of the dribbler using a simulation software, a study of the energy and forces that actuates in the dribbling, both when we are receiving a pass and keeping possession of the ball. And finally, we perform tests in a real competition environment in order to validate our results. In previous works, we can highlight the work by Araújo et al. In 2020, which did an energy balance to design a dribbling dumping mechanism evaluating a pass reception scenario using a simulation software only. In 2019, Wang et al. Proposed a three-touch point dribbler mechanism using simulation analysis and a reinforcement learning algorithm called Deep Determinist Policy Gradient for motor control. Despite its complexity, the work presented good results at high speeds. Our proposed method consists of 4 steps. We start building a 3D model project which generates CAD files of the dribbler. Then we import the model to a simulation software for dynamic analysis. With the results of the energy balance, we can perform a mechanical analysis of the entire system to design a damping mechanism that is able to absorb the kinetic energy from the previous step. Finally, we build the model and validate the results in a real-world environment. Our dribbler has 5 main components: the connector, which aligns the dribbler mechanism. We have side plates, which holds the entire structure. we have the dribbler motor, which is a Maxon SC22 brushless DC motor. The dribbler bar, which is the point of contact between the mechanism and the ball, and the ship kicker, which is primary for kicking the ball but also acts as a third point contact as proposed by Huang in previous section. For the simulation analysis, we used ANSYS finite element analysis software for structural engineering. We imported our CAD model together with a golf ball and we set up all the contacts and real constraints and parameters to design a realistic simulation of the dribbling scenario. The complete setup is described in our paper. For the mechanical analysis, we simplified our problem in a free body diagram to see all forces that act in the dribbling mechanism. Our ball has a fixed radius and weight and a certain angular velocity. Our dribbler has a length and a rotate point relative to the field. The dribbler bar turns also at a certain angular velocity. The dribbler bar must not cover more than 20% of the ball as a ruled competition, and the bar also has a certain weight. As a result of the contacts, we have friction forces from the dribbler bar with the ball, from the ship kick with the ball, and from the ground with the ball. We also have a normal reaction forces acting in each point of contact. We then calculate the ideal distance for a damping mechanism for absorbing all the forces in both X and Y axes of the system together with the simulation analysis. For the energy analysis, we consider the kinetic energy during a puzzle section, the kinetic energy when the robot is in contact with the ball during a dribbling skill, the variation in the gravitational potential energy of the dribbler structure after the collision, and the dissipated kinetic energy after the collision. With all this information, we can calculate the elastic potential of the set of springs that we want to design. Here are a few important parameters that we used in simulation analysis. After running the simulation, we evaluate the ball's kinetic energy over time for a system without springs. Check out how much kinetic energy we need to absorb during an impact of 2.5 meters per second. We can notice that the dribbler absorbs part of the energy and the ball is still moving after the collision. So we can safely design a rear damping system capable of absorbing more than 0.3 joules, while the bottom damping system depends on the gravitational potential energy of the system. We calculated it, measuring the height of the dribbler bar during the previous impact. Due to size restrictions, we substitute a spring system for an EVA copolymer. For the real-world validation, we used Maxon brushless DC motor with PID controller. Our side plates were 3D printed and we tested a few rubber materials, lasting with silicone sealant. We also used double-sided EVA at here and bottom with the calculated dimensions. Here we can check out some real test videos, which are also linked in the paper. In conclusion, we presented a mechanical and dynamic analysis method for dribbling mechanism of an SSL robot. Our dumping system was able to absorb the kinetic energy during an impact and keeps the ball under control. And further works include investigating scenarios of high-speed movements and tests with different dribbler bar shapes. So thank you very much for your attention, and please feel free to ask any questions for us.
Congratulations for your presentation, Victor. We have any questions? Okay, so then I'm going to make some questions. I understood that you use a simulation to select your parameters, but how those parameters were selected? Did that through trial and error, or did you use some kind of methodology or some algorithm?
Most of the parameters are from our real robot. So we had a previous model that we tried to evaluate, and then we used everything that we designed from the previous versions, and we tried just to adjust the parameters for the dumping system for this.
And how you did that? Did you did a lot of simulations and selected the best one?
Yes, we perform, as the simulation takes more 3 or 4 days, so we tried to not run a lot of simulations, but we tried 4 or 5 simulations until we find, and we just did fine adjustments mainly on the dribbler height or the shape of the bar, and these fine adjustments as we lasted with good results on the first 3 or 4, we just tried to perform more, and also from the authors that the evaluators of the paper asked for more simulations, and we tried more as well.
Okay, thank you. Do you want to make any question?
Mm-hmm.
Do you want to make some question? Okay, so I was also curious on how do you put the damping systems on the robots? So how do you implement it physically? I could not understand that.
So with the mechanical analysis that I showed, we tried to annulate the forces, resultant forces. So we found the exactly point where we can annulate the forces of the whole system. Then we put a damping on the back and on the bottom. So we tried to triangulate in the robot that to absorb the impacts with the values that we achieved in the simulation.
Okay.
So it's a very limited size, so we try to fit everything. Then we had to substitute the materials to find it.
Okay, thank you. So I'm going to the next presentation since we don't have time anymore. So the next one is optimizing the vector field navigation parameters using CMAS by Tainá Pires Baldão from Aeronautics Institute of Technology. Tainá, do you prefer to present live or do you prefer to present with the video?
I'd like to play the video presentation, please.
Okay.
Hello everyone, I'm Tainá Baldão, and I'm here to present a work I developed with Professor Marcos Massimo and Professor Takashi Yoneyama called Optimizing Univector Field Navigation Parameters using CMAS. This is the agenda that we'll cover today. We will start with an introduction, followed by an overview of univector field navigation, evolutionary algorithms, and CMAS. Then I'll talk about the methods applied to this work and the results and conclusions obtained. Finally, I'll discuss some future works and give an acknowledgement. To encourage and stimulate research in mobile robotics, several robot soccer competitions are held worldwide, such as the AIII Very Small Size Soccer, VSS. A VSS game is like any soccer match. The winner is the team that scores more goals. The robots can only perform actions based on their communication with a computer. To do so, there is a camera over the field that captures the game images. So, we use computer vision algorithms to process these images and obtain the balls and robots' positions. After acknowledging these positions, a decision-making algorithm decides what each robot should do: defend, attack, and etc. It also decides which is the most appropriate path planning method to achieve the robot's goal. After reaching these decisions, the robot's control system transforms them into something doable by the robot's hardware, computing each robot's wheel speed for the next iteration. Then we send these speeds via radio to the robots. Finally, the robot's firmware processes these messages and takes some action. A path planning method widely used in the VSS League is called univector field navigation. It is based on a well-known idea in path planning: potential fields. This method uses an analogy between a soccer field and a field that contains positive and negative electrical charges. In this field, each robot sees the other robots and the field walls as charges of the same signal, since it intends to avoid collision with these obstacles, and therefore to be repelled from them. In addition, the robot sees the ball as a charge with the opposite signal, since it intends to score goals and therefore to be attracted to it. However, the univector field navigation implementation differs from that of a typical potential field, and we'll discuss the main differences later in this presentation. A downside of univector is that its implementation involves determining 9 heuristic parameters. As the EatAndroids VSS team uses univector as its primary path planning method, we decided to use evolutionary algorithms, particularly CMAS, to obtain an optimized set of univector parameters. We chose to use CMAS because it is one of the best-known black box optimization algorithms. According to OpenAI, it rivals with modern methods of deep reinforcement learning. Also, it has shown excellent results in the robot soccer field. Univector field navigation is composed of 2 fields. The move-to-go univector field is one of them. It combines 2 hyperbolic spiral fields that drive the robot to its destination with the desired angle. The other one is the avoid obstacle univector field, a repulsive field that uses virtual obstacles to predict obstacles' movements and help robots avoid collisions. Evolutionary algorithms are those that provide the user with a set of candidate solutions to evaluate a problem. They are based on the principle of biological evolution, in which mutation and selection of genes are applied to a population to obtain the best individuals. In the context of computing, evolutionary algorithms work like this. First, we randomly generate a population of samples, generally using a normal distribution. Then, while determination criteria are not met, we evaluate a fitness function for each sample, use the fitness values to select the samples for the next iteration, and apply variation operators to transform the selected samples into additional samples from the search space. A simple evolutionary algorithm evolves the population by only adapting the mean of the probability distribution as illustrated in this animation. Even though this approach will work for many problems, it has some downsides, as it maintains the covariance parameter fixed. For example, if we are far from the optimal solution, we'd like to explore more of our search space. Also, if we are confident we are close to an optimal solution, we would like to fine-tune it. However, if we maintain the covariance parameter fixed, we will not be able to spread or shrink our sample to do that. One variant of the evolutionary algorithm is the covariance matrix adaptation evolution strategy, or CMAS. As its name implies, the method's innovation consists of adapting the probability distribution's covariance matrix. This approach is illustrated in this animation. You can see that it has those spread and shrink effects that we want in order to reach better solutions. In this work, we ran 3 CMAS optimization tasks dealing with scenarios with an increasing degree of difficulty. The first task was the no opponents, shown in the recording, in which 2 teammates must score goals as fast as possible without opponents in the field. The second task was the static opponents, in which 2 teammates must score goals as fast as possible with 3 opponents in the field. However, the opponents cannot move. The third task was the dynamic opponents, in which 2 teammates must score goals as fast as possible with 3 opponents playing as an aggressive defense. These tasks were inspired by curriculum learning, a machine learning methodology in which you start the learning process by training the model with easy examples and then gradually increase the task difficulty. CMAS generated samples of univector parameters for the 3 tasks, which were evaluated by running n simulated matches. In each simulation I, we position the teammates and the ball randomly in the lighted field. The fitness function measures the average time in seconds that the teammates take to score a goal in each simulation. And the amount of time that the teammates take to score a goal in the ith simulation is described by TI. The idea behind TI is to punish non-successful simulations. So, if the time required by the teammates to score a goal is lower than Tmax, the maximum time frame of a simulation, TI will be exactly the amount of time the robots took to score the goal. But if TI reaches Tmax without scoring goals, TI will be 1.2 times Tmax. Also, regardless of the simulation time, if the opposing team scores a goal, TI will be 2 times Tmax. Regarding the results, task no opponents evolved 50 generations of populations of size 10, with n equals 10 and Tmax equals 5 seconds. The plot shows the worst, medium, best, and best ever fitness values obtained per generation. The best ever fitness value was around 0.6 seconds. Task static opponents evolved 75 generations of populations of size 10, with n equals 10 and Tmax equals 7 seconds. The best ever fitness value was around 0.63 seconds, a slightly longer time frame than the last task, which we expected given the increased task difficulty. Task dynamic opponents evolved 75 generations of populations of size 10, with n equals 5 and Tmax equals 10 seconds. The best ever fitness value was around 1.26 seconds, a longer time interval than the last task, which we also expected given the increased task difficulty. So, in conclusion, using CMAS in optimization tasks with increasing difficulty, we obtained a set of univector parameters with which 2 teammates performed substantially better in VSS simulated games. They went from not scoring any goals in a 10-second long game simulation to scoring goals in an average time frame of 3.57 seconds. It is also worth mentioning that the It's on Rise VSS team won the 2020 Latin American Robotics Competition using the optimized parameters obtained by this work. In future works, we could apply the same methodology to other optimization tasks or optimize other parameters, like those used in low-level controllers. Or try to perform the same tasks with FIRA-Sim, the game simulator currently used by the VSS League, and even run simulated games in parallel to increase the number of fitness evaluations without increasing the execution time of the optimization algorithm. Finally, I want to thank all the organizations that supported this work, and thank you for your attention.
Thank you for your presentation, Taina. We have time for one question. Does anyone have questions? So, okay, I'm going to make a question. So how do you compare optimization, the kind of optimization that you've done, with reinforcement learning, which is a technique that's used a lot in very small size currently?
I think both techniques are good, but one problem we have is that the studies we have in reinforcement learning are kind of still emerging, and we can't apply normally what we work with reinforcement learning directly with what we have in our current strategies. So I think the type of optimization I did with our works better with our current strategy, and as we know, it kind of currently work really well. It was good to use it, and I think it has a better match with the classical strategy implementations of the VSS League.
Okay, thank you. So we will end the session here since we don't have time anymore. Thank you all very much for doing the session, and all the presenters too. Thank you.
Hello, everyone. We are going to start in a few minutes with Professor Dilma. While that, I was trying to call you for our cultural event that will happen tonight. In the event, we will announce the best papers of LARS, including the ones that we have selected for being submitted to the Journal of Intelligent and Robotic Systems. The best papers, the best students prizes of the double TDR and CTDR will be released on Thursday afternoon. So they won't be tonight. Tonight we will have some musicians playing, and we will be happy if you could get together with us, mainly to see these musicians and also the best papers that will be released. Julio, as far as Professor Dima is okay, you can get back into here, okay? Thank you.
Hello.
Hello, Professor.
Yes, hello, Eduardo. How are you?
Yeah, guten Morgen.
Good morning. So, okay. So I can't see you, Eduardo, but you are there. Okay.
Yeah.
Hello. How are you?
Hello.
Good to see you.
Fine, thank you. I hope you will be able to share your screen.
Yes, I have done it already, and I can try again. So, do you have it now?
Yes, we have it.
Yeah.
Great.
Okay, then I can start.
Okay.
Hello, everyone. First, I want to apologize to everyone, and especially to Professor Dulman for this delay. We had some technical issues, but everything is okay now. So, continuing our second day of LARS, we have the keynote speak now. This presentation from Professor Dulman. It's titled Building Brain for Robots, Neuromorphic SNN-based control for robots' visual motor tasks. I will briefly introduce Professor Dillman. Professor Dillman began his academic journey in 1976 when he got his degree in electrical engineering in the University of Karlsruhe, Germany. And in the same university, he obtained his PhD in 1980, and in 1987, he became a full professor. Over the years, Professor Dillman has coordinated several research projects in the area of robotics, automation, and related areas. He is also the author and co-author of more than 1,000 scientific publications and has published several books and also is the contributor of several books. All of his publications amount to more than 20,000 citations, and Professor Dillman is an IEEE Fellow and also an IROS Fellow. So again, welcome, Professor Dillman. Sorry for the delay, and thank you very much for accepting our invitation.
Thank you very much for this kind introduction. I want to thank you all that I have been invited to Latin American Conference on Robotics. I think in one of the first one I participated, it was in Mexico City, but it's a long time ago. And thank you very much for the invitation. So the topic of my talk is to discuss some ideas, new ideas, how to build robots in form of robot brains. We had in Europe a very large project, the Human Brain Project. It's a flagship 10 years program. And what we do is to understand how the brain works, what are the basic principles to learn from that, and to implement controls following this functional unit derived from biology, brain research, chemistry, and of course, neuroscience and informatics. So starting to look to the past, here you see some engines. We built them early to test neural networks. At the upper left side, this was one of our first 6-leg walking machines with classical networks. They have been used to move individual legs and to coordinate legs, and then to add on top some camera systems to walk in uneven terrain, to generate maps and to get experience from the environment. At the right side, you see the next machine. The first one we built by wood, because at the beginning we had no money, and then we built it on a very primitive level, the system. And then later on, we had aluminium and other materials to build the systems. I think Eduardo thought he did work with this machine for his thesis for pattern recognition and studying the saliencies to understand better the environment. Then four-legged engines. What is interesting in these machines that you have to control a high number of actuators, a high number of sensors from the legs for angle measuring, velocity, body balancing, also cameras to perceive the environment, and also using sonars to make experiments in the test beds. Also, the actuators did change during the time. We had pneumatic drives. Here you see the left upper side, a robot with artificial muscles. For each joint, you need a pair of muscles to control both direction of joint movement. And then, of course, at the right lower side, you see a machine which has already four-stroke sensors in the feet, haptics, odometry, and also some possibility to measure gravity, so to balance the body so that it's not falling down. Okay, let's go to the next one. Looking to other autonomous systems where this basic technology has been developed, you see at the left side a fully autonomous robot system with omnidirectional platform, 2 arms. This has been developed for manufacturing environment. And then the first hands which have been developed with biologic principles. One is a 3-finger hand, then you see here 5-finger hand, and then the first models of a humanoid robot, which has been designed, followed by further development of humanoid robots. We had tested their microfluidics, micropneumatics, but also electric drives, and implemented it for 5-finger hands to be able to grasp and to act in the environment like humans are doing that. The idea was that for that to, instead of programming, building heavy models, was to demonstrate, to show to the robot by a human how to do something, how to grasp, how to move, and how to position the elements in the objects in the environment. Here you see indoor application. This was a kitchen. Still today we are working in the kitchen, not only loading the dishwasher, but also cleaning and cooking and preparing the dish. Next step here, you see 2 robots interacting autonomously, so they can cooperate together using 4 5-finger hands and using for grasping, interacting in non-coupled and in a coupled way. And there you see some novelties. At the left side in the large image with the 2 robots, the blue part here of this robot is an artificial skin, so that humans can touch the robot, push them away or guide them to follow, and then some cognitive capabilities have been implemented on this system. One, to identify the task, to identify the situation and the objects, and then to decide to do the right action and then to execute this action. These are cognitive capabilities, and they are very close to learning. You can learn from models with heuristics, rules, but actually it's also possible to follow data-driven learning approaches like deep learning, where a lot of data is used to learn and to classify and to act in the right way. Looking at the basic problems you see here is that looking first to programming of such complex systems. One problem here is if you want to do a textual programming, then teaching and code writing is one possibility. The big problem you have here is that in case you modify the program, you have to rewrite everything. Next step here are flexible programs where semi-symbolic programming is used with variables and with symbolic descriptions. And this can be extended, of course, to hierarchical representations. A typical part is finite state automats or task networks, which allow to describe the action of robots. Okay, using AI as we do that today, it's possible to generate in a flexible way programs for grasping, for motion, for obstacle avoidance, and to use planners. They operate on grounded knowledge. They operate on models and also on perceived data of the environment. Pre-programmed skills is one way. The pre-programmed skills, they follow the ROS philosophy to have libraries of skills, to connect them with a strategy graph, and then it's possible to generate programs with the help of libraries and to generalize them, of course. A complete alternative is to use artificial neural nets and to do their decision-making, but also some reasoning about the environment of the system. So going to the first idea, all these methods I presented have advantage and disadvantage. And the other one is to have really flexible and learning structures. We go back to the brain. And here, the problem is to understand functional components in the brain. And on the other side, to translate these controls onto neuromorphic computer systems. They run usually a high number of neurons, spiking neurons, and you can use its plasticity to modify the weights and to modify also the synapses, which means the connectivity between different neurons. Actually, on the market, we have low power chips with extreme short time delays or short latency, which are available from companies. There are also research hardware, neuromorphic hardware under design. Big advantage is low power consumption in case of using spiking systems, and then to implement neural controls, which are based on plasticity, on connectivity, as I mentioned already. Going further to that, it's important that vision or visual motoric skills have to be implemented in the brain. There are the eyes. There is one part in the brain processing data from the eyes. This is and then to connect it with the motoric parts. We call that visual motoric skills. To integrate them, connect them with a motor system, and to have an information on the event flow, which based on spikes over time. Spikes have some advantages, I will say you later. The advantage of using spikes is that you need no more code, you only have spikes. These are pulses, and they are weighted with 1 or with -1. You can trigger events with that in the right time, and you can memorize success and failure in terms of reinforcement learning. Usually it is done in a hierarchical way so that you have different levels to apply this reinforcement strategy. And the next one, which is important, is that these multi-level controls allow also to build spiking neural networks for control and to have mechanisms to adapt them, to extend them, and to have a generic representation of activities. Assumptions which have to be done, and problems is how to memorize in spiking neural networks information. So In case of reinforcement learning, short-term memory and long-term memory is necessary to have a kind of episodes which can be stored in this structure, where backpropagation is possible, and that they can adapt to changing parameters of the environment, and to optimize, to have better visual motor skills. One part which is important is that natural neurons are very slow in comparison to our computer systems. If you look what a GPU can process today, the neurons are really very slow. They fire at frequencies of about 100 Hertz, which is extremely, but we have thousands of them, which can be exploited. And the synaptics, the weight of the synapse is called synaptic plasticity, can be applied in the sense of reinforcement. Okay, the operations for spiking neural networks are to have these leaky integration and fire rules. What you have for one neuron, I show it later, is that you integrate the input, there's a threshold, you compare, and damping, of course, is there in addition, and then the neuron is firing, but firing only one neuron. Okay, from biology and neuroscience, more details can be derived for them, but the neurons I discussed today, they are very simple one, which operate at low frequency. Here in this image, you see, if you compare the brain with today's processors, which have very high data flow and frequency, it's extremely small, but the density of the neurons in the brain, and especially their connectivity, is very high. So we have a high number of parallel distributed devices, neurons, with local connectivity and with connections, wirings between them, interaction with them and with the environment, and then this spatiotemporal pattern, which are processes with that. Here's some examples from nature, which shows the number of neurons which can be observed. You see an ant which has an extremely low number, but the ant has a very efficient set of behavior, operates sexually. The bean is shown here, a cockroach, and then the mouse. Mouse has one basic structure, similar brain functionalities as humans. It has about 75 million neurons, and if we go to the human, we have billions of neurons and higher number of synapses, so it's an extreme connectivity which you can observe. Both the human brain and the brain of the mouse have been studied. There exist atlases with where you can see it's a map of the brain from the mouse, and also from the human brain, which is very important to study structures. In the human brain project, you see all these topics have been studied, starting from the molecular level of neurons, how they principally work, by what they are influenced, by chemical influences, hormones, temperature, and ions. And then you can look to cells. This is a functionality of one neuron or two neurons, how they interact. And this, what is interesting for us are the circuits, functional circuits, which have input, output, and which support the visual part, the motoric parts, and others. And then you can go forward to look for regions. So with MRTs and with CT MRTs, they are studied. You can identify regions which are active in certain activities. And then, of course, the functionality of the whole organ is of interest. So in the Human Brain Project, the basic functionalities have been studied, but also disease of human brains are under study so that disturbances or disease can be identified, observed, and maybe a therapy can be designed. On the other side, we look to the disciplines. Neuroscience is important. Medicine has different aspects to identify diseases. And from our side, computing and robotics is the part which have been studied in the Human Brain Project. So the idea is to have a brain and to connect it with robots, as you see here. And then you see here one simulation there from the Atlas University in Geneva, in the Biocenter. They implemented this network of neurons, and they are stimulated, and the reaction to the stimuli are shown here in different colors. So you see there are waves, there are activations coming from the outside, and which initialize activities in the brain. From technical point, if we look to individual neural nets, as it is shown here, you see the biologic principles at the left side. We have the axons, we have the synapses, we have the nucleus of a neuron, and this is coded with spikes. There are spiking signals as input, and there are spiking signals at output. And in the middle, you see it's in the integrate and fire a neuron. It's a relatively simple one. You need an amplifier, a capacitor, and then the input, and this is integrated on the capacitor. And if it reaches the threshold, the cell is firing, as you see here on the right side. Here are some examples. We have input. These are maybe currents. Then they are integrated. These are the presynaptic spike trains, and then you see the spikes, the output spikes at the lower side here, where we get at the right instant, if you reach the threshold, only one spike. So you need no bits and bytes and coding and algorithms. You only need this very simple integrate and fire neuron generating from this input these spikes at the right time. And advantage here is that the noise ratio is low, and the memory, here's no memory necessary. It's directly communicated to the next neurons, which are here. This is one structure of a classical neural network. We know them with several levels, different architectures with input and output. And here you see a spiking network where the connectivity is much more higher. You have an input flow and the output flow in terms of spikes, which are seen here. This is one example to show how it works with the input signals generating the fire and spikes. They are processed within the network. It's a flow, direct flow from neuron to neuron. And at a lower level, you see the output of this network, which shows spikes according the input signals and the processing rules which are necessary. You can implement it directly on hardware with digital processors or with analog processors, integrators, for example, with chips, which have 10,000 or more analog amplifiers or processing units which integrate and fire in a digital way. Neurons are not new. This type of neurons are not invented. They are not new. There is very early work where spiking neurons have been discovered by Louis Lapicque, making experiments with neurons. The first models of neural networks in this direction was in the mid of the last century, where in the domain of biocybernetics, some models have been developed, and then artificial intelligence has been introduced at the time, which is going in a which went at that time in a quite different direction of processing information. Yeah, biological spike propagation is known by Hodgkin and Huxley. I think everyone working with spiking neurons is studying this work. And then today we know a wide variety of neurons which are modeled with coming closer to biologic models and which can be handled in a high number. Here's some examples where demonstrators have been implemented. I think IBM True North is one known processor, which is digital and which has been used. If you look to the power consumption of the system, it's about 200 milliwatt, which is rather low compared to traditional and compatible systems. Intel is building a system with spiking neural networks using an analog processor, as Intel Loihi, and this is used for different kinds of applications, mainly visual processing, but also for robot application and simulation. And then one special analog processor has been developed, which is an ultra low power architecture from a startup company coming out of ATH Zurich, where they have event-driven cameras and developed an adequate processor which is used. The power consumption is very, very low. You see here this Zurich chip, it's 1 milliwatt, and which shows how impressive that is. Here you show how biologic vision is. This has been a study which has been done and published in Nature. So in the images you see here, a lot of faces are hidden, but the human brain neural structures are able to identify some. And if you have an event-driven camera, you can observe them completely and classify. So the cameras, which have a very good interface to spiking neural nets, these are the so-called event-driven cameras we have here. They are built close to the human retina. These are receptors. If there are photons, they are activated and fire signals to the brain. In classical cameras, you need frame grabbing. This means to read out a complete image from the camera and to store it, and then you can start processing it according to what you want to do with that. If you have a DVS camera, you have only events, and each event is marked by one spike at a very small time resolution in microseconds. And you can observe if something happens in the environment, then you get this only in case of an intensity change value, you get a spike. I show you what is the consequence of that. It has a lot of advantages how to use this camera. So the representation of the event, we have, of course, the time. We have the pixel from which, what are the coordinates of the camera firing with a pixel and the spikes. And then the polarity is here shown, I mentioned already, +1, -1. This shows how this model is. You have here a distribution on this intensity on the signals. And then you can work, study with, according to the intensity, +1 and -1. The dynamic value, if the value is changing. So you see here in the curve, we have off and on. And then you get here a series of spikes working like that. Okay, Here, blue is negative direction, red is positive direction of changing of the intensity. And if you look to the camera now, this event camera, you see in the movement after 10 milliseconds, the moving hand in front of the camera. And on the level of that, you can process and identify with the spikes very quickly and with a high sample rate movements. This is the basic principle of this event camera.
That it doesn't shake like crazy.
Here you see the environment of one room. What is done here is that the dynamic events are from the moving camera. It's something like saccades, that the eye is moving, and then you get events for each pixel showing what happens in the environment. Cameras which work on this resolution and on this event cameras are shown here. There are some which work at megahertz, but they have a low pixel number, but high speed, and the data rate is rather high, you see here. Standard camera in comparison is to seen here in the middle way. We have megapixels per camera. Bits per pixel is 8 or 10 bits which are processed. The weight is light, and you have a data rate which is impressive, and 1 watt is a consumption of such systems, and here also the dynamic range is rather high. Event cameras are shown here. They work with 1 megahertz, and resolution is up to 1 megapixels today. We have bits per pixel. These are the spikes which are used here. Lightweight is necessary. And if you look again to the power consumption, we have 1 milliwatt of these systems, only to give you an idea. So the potential, if you want to build controls for robots with event cameras exploding spikes, is that they are in time, no time delay, it's low power, they have a high dynamic range, output is coded, of course, in spikes, and no motion blur is to be observed. Here, one example. You have such a camera which is moving. We call that a saccadic moving to the right. You can rotate, you go to the left or to the right. And only when it moves, you get on the events on the event camera, which is shown in colors on the right side. You can move the camera, for example, to map an environment, which is shown here. Exploiting here the gradients and the difference on each pixels, so they are detected as an event. And then you can use that for reconstructing the environment on the basis of the input events, as you see here at the left side, at the upper left side, which is used. And then from that, you can reconstruct the environment, as you see here in the lowest row, where from the first way point clouds are generated, and from them the color and the scene, the intensity image can be reconstructed as a depth image. So if you go back to our robots, we have this approach to have cameras, the eyes, as you see here. To use these event-driven cameras has a lot of, in this study, as a good interface to the brain itself. And there is neuromorphic hardware. This is a multiprocessor board which has a spinnaker. It's a spinnaker board. It has been invented in England. And there are boards today up to 100,000 of neurons. This is not analog processing, the neurons are implemented in a digital way. Then the robot, this means according to the visual information, the robot is acting to craft, to do something, as you will see later. So from computational neuroscience, we are taking models of brains, or to how to process clusters of brains, for modeling motion primitives, to have a structural plasticity, to recognize the environment, to have learning mechanism as it's shown in a liquid state machine, and then on the other side, a structural plasticity for event-driven backpropagation methods. Here you see one experiment of a moving image, and with the classical camera you can do that, of course. You have to sample all pixels with high speed and to process that. With event-driven camera, you have only these individual spikes according to the intensity change we have here. Oh, it's growing here, it's decreasing, plus and minus spikes, which are to be used. The mechanism here is, here you see a camera. Of course, the camera can be moved, so we can rotate it to the left, to the right. These are our saccades, so with 2 axes or 3 axes, and then you can observe stationary environments. What we want to do here is, of course, to identify objects. For one example, this means labeling is important. What is a typical spike structure of objects? We identify errors. We have an extra channel to minimize the errors. And then a neural network starting up for training. This means we have identified objects, pre-classified objects, observe them with the camera. We start with labeling, looking for the errors we observe here. And then in the second step, we implement it in a real-time system. This is a stereo camera system and manipulator, 5-finger hand, where we can learn identifying objects and grasping that. Behind that are, of course, different neurons. We have here different types of synapses. The blue one are inhibitory synapses. The red one, excitatory synapses. You can model them, for example, with the help of a liquid state machine. And there are neurons we call label neurons for teaching, learning, and later for classifying, error neurons, and then on the other side, learning neurons and neurons building the output. So what you see here is a short movie where this camera is demonstrated. Here you see again the structure. We have the pixel camera, and then the training phase, for example. This is the camera. You see the moving arm. These are the pixels, blue and red. Here we have a stationary obstacle, so the camera has to move. So if the camera moves and generates microsaccades, you see the pixels at the right upper side in this image. Okay, this has been done for different objects. To teach them, to learn them, you can also observe the background to optimize, to map them also if you need a 3D representation and so forth. Okay, let's go through. If you have taught these objects, you can make the experiments. The experiment is seen here, the 5-finger arm, the 5-finger hand with a robot. The object which is observed here with saccades, and then the saccades are processed to the robot itself. First it's classifying the object, and then it generates a trajectory for grasping that. Everything done on a spiking level to show that. Okay, two control loops are, one is to minimize the errors. The second one is to optimize and to adapt to different objects in these experiments. Okay, the mechanism which has been exploited here is this backpropagation algorithm in the networks. Here, errors are backpropagated not from the outside to the input, but we have it also on different intermediate levels where errors are predicted and then compensated in these systems. So this has been published. There are several papers which have been shown. Results, hand motions on different subjects to be classified. This is IBM dataset where we tested our methods to be to compare our results with others. The hardware system you see here, again, the camera, the spiking network processing the spikes themselves. Then we have this Intel neural network neuromorphic chip, the LARS system, and with that one we generate the classification, analyze the motion, and label them. So these are some results of the accuracy we could achieve. 100% classification we didn't reach, but we have here recognition rate, I think, higher than 95%. You can also use this camera for stereo. If you have two cameras like the human eye, you see the camera right and left, and there is the problem of this disparity and the correlation between left and right eye if there are moving events. And then you have event stream from one camera from the right and the left one, increasing, decreasing, and then you can correlate both. And this you can use if there is a correspondence or correct correspondence. You can use that for 3D construction. We use that in experiments to generate with this stereo event camera structure to classify the environment of a robot, to have a 3D neural memory. And in this memory, of interest now, of course, the objects, the robot itself, and the human who is a potential collision object if there is interaction necessary. There's the other one that finally in the talk, I have to speed up, sorry, is that how human motion can be mapped to the robot itself. It's programming by demonstration to take a camera observing human activities, to segment the activities to a human model, and then to simulate it on a target system, this is in case a robot, and then to execute it as it has been done in the Human Brain Project. Here you see how motor primitives can be coded. You see here activation input where excitatory signals are given to start the motion. A network is initialized, the weights are determined, and then it's possible to execute this movement only on spike. No, there is no coordinate transformation in this application. The space for these robots are on the joint level. So it's joint space. Nature has the force space, and we are exploiting that. So what is possible is that different motions can be generated in this type. For example, to have a free motion, to have reflexes. Reflexes must happen very fast. There's no planning, trajectory planning used there, only to classify and to move in the right direction. Repetitive motions, rhythmic motions, which are seen here. There are some examples how the spikes are looking like and how this can be used. The reflexes are using sensor input from the robot. We call that proprioception. So if there is high temperature or an obstacle, the robot stops immediately and goes back as a reflex. So time is too short to go deeper, but also here we have a wide variety of experiments. For example, here we learn basic motion primitives. So the robot has to reach in this area where we have to circle different points. One is to reach at the center. We can generate dynamic motion primitives and arrow functions, which are minimizing that. You see this here. Each block here is a neural population, cell population, and you see the basic motion primitives, motion control commands, and the corrective motions, which support to have the right motions and to meet the target. Okay, these have been experiments we have done to measure the accuracy of this method. It's only one net which can generate all motions on this plane to reach points as shown here. The error analysis is to seen here. If you do this, I think the evaluation is very important. And this is finally one application where we make studies with the hand, with a myosensor, and there we observe muscle activities, and then we map it on a neural network and replicate it on a 5-finger hand, showing individual movement and reflexes which are of interest. But we do it also for grasping. If you want to implement a 5-finger hand, for example, you have to activate first from higher brain areas different grasps, a cylinder, a sphere, then a 2-finger precision grasp. You need a thumb, the individual fingers, which have to be activated. These are all neural networks. Then the reflex area in case of contact. And then there is the output, which is controlling the individual or controlling the individual finger movements. Control loops, of course, are here, measuring currencies of the motors or forces or the efforts, and to build then to close the loop in this way. This is one experiment which has been done to grasp stiff and elastic objects. In this experiment, grasping the bottle, grasping a very elastic object, activating the type of grasp and the fingers, and detecting the feedback of the haptic parts of the finger movement. Okay, time is too short to go to details. Of course, you can see what are the errors of the control loop, how to optimize them, and look if it converges to stability. Finally, this has been applied to physical robots, a walking machine, as you see here. Each leg is controlled by a neural net. Then we have the coordination of the legs and then balancing of the body. You see here the different controls for coordination and for individual leg movement and the camera. And finally, it's possible to have experiments. What you see here is the so-called Breitenberg experiment, where we have a virtual sensor and the robot is going direction of colors, color changings, and is moving around. This Breitenberg vehicle experiment is to check visomotoric approaches. Real applications you see here. We apply walking machines now in field experiments. At the left side, these photos I made last week in Stuttgart, in Germany. We had 2 robots. All other robots you have seen, we built ourselves. These are robots we use from Boston Dynamics and from a Swiss company. And they are applied to map the environment of Fairground. It was the MOTEC in Stuttgart last week. And on the right side, you see applications of these robots. This is in field applications for cutting down nuclear power plants. You see a robot house, a heavy machine for automatic carving. There's no human on that. You see these walking machines, the walking machine with a laser sensor mapping the environment. Spot equipped with sensors has to coordinate both the truck and the carving engine, heavy carving engine. And this is to manipulate. This is a simple four-wheeled sensor, which is searching for objects and to find them and to grasp them. Okay, last words to the hardware, which is available now for biomorphic systems and biomorphic computation in areas of vision, motorics, navigation with spiking neural nets. There is a Spinnaker system. BrainScales is an analog computer developed at the University of Heidelberg. True North and the Intel system all are working on the next generation with millions of neurons on the chips. So that here you see where how the future looks like. Spinnaker is able to have about 1 billion neurons in clusters. Energy is relatively high, can learn, it's digitally implemented. BrainScales is an analog computer. BrainScale 2 is going to 1 million and more neurons, and the adequate synapses. True North is also, but interesting if you look to the energy per device. Spinnaker has high energy consumption actually, but the other one are all smaller than 1 watt and have this extreme high parallelism. Okay, with that I come to the end of my talk, and I thank you very much for your interest.
Thank you, Professor Dillman. Do you have some more time for questions?
Yes, of course, I reserved the time for you. Initially, I intended to come to Brazil, but unfortunately, it was not possible. So I'm maybe the next time this can be done.
Next time you will be very welcome to visit us in person. So we have one question from YouTube. I will start with this. Leonardo Amaral Vidal asked, can you explain how the training steps work in this SNN implementation? Thank you and congratulations for your presentation.
The control loops we are using.
I think it's about the training of this type of SNN.
Yes, first of all, we have to train the system. To give examples, then to simulate and to generate the first rough feed-forward movement. At the same side, we need a corrective function. We have to initialize the corrective function, and then we train in simulation, and then we use this structure in the target system. And in the target system, we have also a feedback and control loop to make the system over time better. And this is a kind of reinforcement we are using. At the moment, we have external sensors to evaluate the accuracy of the movement. But the goal is not to have a super precise accuracy of industrial robots, which work in the sub-millimeter area. In nature, we have rough movements. They are predictive, and we have feedback over the eyes and over the haptic system, which enables us to have 2 or 3 control loops. And with this plasticity of the neurons, it's possible to switch from a position controller to a movement controller or to an elastic controller or non-linear controller. This means with neurons, you can implement in structural terms a structure variable adaptive system. And this is the big advantage. And humans in biologic systems, we have a lot of controllers we can activate according what we are doing. Walking, to manipulate something with fingers, or to have a macro motion. And then it's a difference if you play tennis, or if you do an assembly, or if you play soccer. You need different controllers. And humans have a big repertoire of these controllers. They are activated according to the context, and then, of course, optimized with training. If you want to play tennis, you must train and to reduce the error function, and to have a high variability and a very fast reaction. And this fast reaction you can store in the neural network using this multi-level reinforcement learning. That's the idea. This means to build control loops, first to start predictive, to train, and then to go to the target application and to optimize the system. To compete with humans, it's very far, if ever we will be able to do that. And one part of this work is also used for rehabilitation. So to reactivate muscles, hand movement, arm movement with this technology.
Very interesting. I have a question. What are the limitations of the SNN or some kind of SNN-based architecture?
This is programming. You need programming. Of course, there are some tools where you can use program SNNs, the topology. You can start with supercomputing to modify the weight of the synapses. If you have thousands or millions of synapses, you need big effort of time. And to program now in terms of engineering neurons, this is what we are looking for. This is actually low-level programming. You must go to the motor level of the robot, building the neural circuits. But if you have them once, you can activate and deactivate them, and you are very flexible. So programming and software engineering tools, some are available. We are actually not very happy, but there are some platforms which support that from IBM, from Intel, and also from the University of Heidelberg. And from the Human Brain Project, there is a neuro platform which can be accessed. It's open for everyone. And I can send you the access code, how to do it. The idea in this neuro-robotic platform is to offer people worldwide to make its own experience and to learn how to work with them. We have done that with students for practice, and after 1 week they have been able to work with this technology and to implement nice applications.
Okay, do we have more questions from the audience?
Oh, see. I have to apologize that we had the technical problems. So maybe it was my side or both sides, but we found that. Sorry for the delay. Oh.
I have one.
Okay, Gilles.
Yeah. It's a very impressive work, actually. It's, for me, it's very hard to get in touch with this kind of work, because I'm more on the programmer side of the technology. So I really like to control things. I'm very controlistic. And I have maybe a more philosophical question. Are we in the position to really control those systems, or we are just teaching them and then we don't know anymore what are they doing? I mean, do you really program those, or we are just teaching them and then they are just acting for themselves?
So we are starting, of course, in a systematic way, first to have motion primitives, dynamic motion primitives, to make simple movement and complex movement together. We study the mechanism, and we have to learn it for each application. We are far from that such a robot can learn itself complete new things. Humans can do that. They need one example, and they can translate it in another context. And then learns. If you observe small children and how they learn, and they learn extremely fast. And so we have first motion, grasps, and made the studies on the event camera, on the but a lot of other problems which are not done. One is, for example, how to evaluate a situation where is focus of interest, where you have to look to what you have to do. So we are starting with simple experiments, with studying basic principles and scaling up the brain to have these six-legged walking machines where we have to coordinate a lot of jobs. Then for grasping and including reflexes, this is one. And reasoning. To understand what is going around, as Professor Burkhardt yesterday gave in his talk, there we are far from that. Resolution is that you build maybe such a reasoning system as you are doing that today, and you connect it with these neural controls on the lower level. Because we don't know how the higher brain level works, it's too complex. And we only know functional parts of the brain. And these we are replicating and to apply to robots. And hybrid systems means that you can have this high-level planning, decision, or cognitive part, and then to connect it with neural levels. What is advantageous for us is that we learn on the joint level. There's no coordinate transformations, no inverse robot, and all this type, but we have to store it in our neural populations. And we show that it is possible to have one population of neurons, let's say 1,000, and we can memorize there a lot of motions of a certain type. Then we have another population where we have the motion of the hand, or the individual fingers, and we build with them hierarchically systems.
Okay, thank you very much.
I can send to Eduardo a PDF file of my talk, so that you can use it and distribute it if you want it.
Of course. Thank you, Professor. We appreciate it. I think Professor Eduardo has a question for you.
Mm-hmm.
Yes, thank you very much. I appreciated very much your talk. Thank you. I would like to ask you, do you presented research that is much closer to biological models than the current technology that we are using? Do you see that with these low power neuron chips and this kind of things, we are approaching revolution like we saw with the artificial neural networks and deep learning with GPUs? Do you see another breakthrough in the few years?
That's my motivation I do in my old days to go forward to this field. Of course, the robot community will publish that. And big critics in the community is how you compare with competitive and numerical approaches, working on the Cartesian level, calculating the transformation. But if you look to the amount of energy you need for training of them, if you look the complexity of the robots, if you look to our humanoid robot I showed you, this is the ARMA 3, and we have now the ARMA 6 generation built by Taminatsfur. You have more than 60 motors. And if you have an algorithm and to program that and to combine that, this is absolutely cumbersome. And to make them more soft and to coordinate, this is an alternative. The number of publication on spiking neurons is increasing in pattern recognition, in cognitive perception of the environment, in dynamic environment. We applied this control to, in simulation, to run an autonomous cars following a lane and stopping in times. In the lane, you can accelerate, going to the right, to the left. So the behavior is not so big, but we trained this simple network I showed in the Breitenberg experiment. We made, of course, with cars. And there are now car manufacturers, of course, they are looking to that because they have chips which are power, they hope to have low power systems on their car with a high variability. So it's a new technology. I think it's interesting. Personally, I think we first tried to understand biology. Biology is simple but very efficient. Everything which is not working, they don't survive. And if you look to the neural networks, it's really simple. And nature did build then brains which allow animals to adapt. And so it's an alternative. I think if we have low energy in mind, these biomorphic chips, but we have to learn how to program these systems. Nature is building that with a genetic code, and this is not understood how the nervous system is coded in DNA. So I think this is magic for me. But I think coding, the first tools are available to program spiking networks, to build controllers, and analog or digital chips who can do both. I believe, personally, I think that analog computing is the right way, because it's a new way of analog computing with spikes, not with analog signals, where you can build directly implement differential equations on neurons to integrate, to multiply, subtract, to add, to have nonlinearities, and you connect the controls with the synapses and the weights, and you can eliminate a controller by having high weights, so there is no signal going through the neuron. And it's a way of analog adaptive systems. And so I think theory of adaptive systems, if you know the equations, you can go to the neural networks. And with neurons, you can process a high number of differential equations, and that's the reason why I think that this works, if you come from both sides, from theory and from biology.
Mm-hmm. Great, thank you.
Okay, everyone, I think we can stop now with the questions. So again, thank you, Professor Dilma, for this excellent presentation.
Thank you. And you have now lunchtime?
Yes, we're waiting to eat something.
Okay,
So
well, thank you very much for the interest. And I sent to Eduardo this PDF file. With the movies, it's too long. I think when he comes to Switzerland, he has to visit me. Then he can have the movies.
Okay. So I think we go now to lunch break, and then we think it's 2 p.m. and it's over. Julio, can you help me?
Okay. Thank you very much. Goodbye.
Goodbye, Professor.
Yeah, bye, Professor. Yeah, it's 2 p.m. We are going. We are back.
Okay.
Thanks.
Okay.
Thanks, everyone. Professor, you are invited to the rest of the conference if you want.
Okay. Thank you very much. Bye-bye.
Very nice talk. Thanks, Todd, if you are still there, for inviting Professor
Yes.
Dilma.
Okay.
Many good talk. Not only him, but also Professor Carmen tomorrow and the yesterday one. I think the three of them you invited, right?
Yep.
Yeah, thank you very much. High, top level. Julio, I want to be back here at 2 p.m. because I have some